So far, we have studied compound propositions. We studied how AND works, how NOT works, how implies and biequivalence works, and finally, we looked at a lot of logical equivalences and did examples of logical equivalences, which are the laws of propositional logic and involve like De Morgan's laws and double negation. But now, notice that nowhere in here do we have any variables. And we do need variables to be able to express mathematics. So propositional logic does not have enough expressive power for mathematics. And this brings us to the next piece of logic, which does have variables, and that is predicate logic. And a predicate is nothing but a proposition that depends on a variable. So when we say that a proposition depends on a new variable, we have to be very precise about how we introduce a new variable. And to introduce variables in predicate logic, we need three components. The first one is obvious, is the name of the variable. The second one is the domain. And the third is the quantifier. And the quantifier, if you haven't seen any math proofs before, which I expect most of you haven't, quantifier is going to be the newest mathematical concept we learned here. Okay, so variable name is just the name of the variable. What is the domain? The domain is essentially all the possible values that the variable could potentially take. So I would just write this as where is the variable? So reals, integers, natural numbers. It could be a finite set, so it could be something like just 1, 2, 3. It could be an infinite set, so it could be 1, 2, 3, 4. It could be an interval, where I'm thinking of the interval as a subset of the real numbers, and so on and so forth. So a domain can be any set. You don't need to know what a set is precisely, as long as you roughly understand what it is. We'll come to the definition of set in the next chapter. That's what a domain is. It's the possible values that the variable can take. That's another way of putting it, so maybe I should write that down. It's the possible values. And finally, now we come to the quantifier. The quantifier, okay, this is completely new, so I need to introduce a lot of math for this. There are quantifiers. There are exactly two quantifiers. There is one called the universal quantifier, and then there is one called the existential quantifier. And what is the universal quantifier? Has the symbol upside down A, and the existential quantifier has the symbol of capital E flipped. So that's the universal quantifier and the existential quantifier. And what do they mean? So you write this as for all x or for there exists x. So you put them in front of the variable, and then you put the proposition in the front, or you put the predicate in the front. So this is how you write quantifiers. This is how you write predicates. You start with the quantifier, then you variable name, then the predicate, and the domain you have to state somewhere else. So the domain is already stated. And this statement translates to Px is true for all x in the domain. And the second one parses as Px is true for some x in the domain. The second one is also often written as there exists x for which in the domain for which px is true. So these are the definitions. The universal quantifier is used to express statements of the form something is true for all the variables in the domain, and existential quantifier is used to express statements of the form something is true for at least one variable in the domain. And this is enough to express all of mathematics. You don't need anything more, which is really surprising, but amazingly useful fact. Okay, so these are existential and universal quantifiers. And why is this called universal? I don't really have a good answer. Often people call this the for all quantifier. So this symbol, you will see more often people using for all rather than universal. And similarly, this symbol is parsed as there exists x. Yeah, and you can see that in the words here. For all shows up here, and there exists shows up here. Let's do some examples. Let's start with some true examples. So I can say let domain be natural numbers. Then I can create a statement for all x plus 1 is greater than x. This is true for all natural numbers, and so this is a true statement. I'll come to false statements in a minute. I can have also said that there exists an x such that x plus 1 is greater than x. And this is also true because there does exist at least one x for which this is true. It is true for all of them, but that's fine because it is true for one of them. Similarly, I can now let's do a false one for all x. X plus 1 is equal to 2x. This is saying that no matter what natural number I pick, x plus 1 is 2x. Let's check, is this true? For this to be true, it has to be true for all x. It has to be true for all natural numbers. Now let's see if that happens. Let's start with the first natural number. We usually do start with 0 for natural numbers. So 0 plus 1 is equal to 2 times 0 gives you 1 is equal to 0, and this is false. So the first example itself fails, and so this is false. It's not true for all. Here's an example. What about there exists? So now I'm asking, does there exist one x within the domain of natural numbers such that x plus 1 is 2x? So now I don't care about all of them. So can I find one x? And I can do that by just solving. Use a different color. And yeah, x equal to 1 works. I could have just like plugged in x equals to 1 and saw if it worked without any algebra. And because there exists one such x, the statement is true. So that is there exists quantifier. Now let me emphasize that things depend a lot on the domain. So let me change the domain and let's do a different problem. So now let's look at, or let me, here's a nice example. I know one more. So let's consider there exists an x such that 2x is equal to 1. Okay, so right now our domain is natural numbers. Is this true? So now I'm asking, can I find an x such that 2x is equal to 1 within natural numbers? And the answer is no. In natural numbers, there is no such x. So this statement is false. Now let me change the domain to real. numbers. And I'll take the exact same statement. There exists an x such that 2x is equal to 1. And now can I find x in real numbers such that 2x is equal to 1? And yes, I can divide both sides by 2. X equals to half is a valid real number, and this works. And so this statement, upon changing the domain, becomes true. So that's how predicates depend on domains and how you put them. So it's quantifier, variable, and then predicate. Now, doing these exercises, we came upon some principles for proving statements about quantifiers. So let me start with the universal one. And if you want to show that a universally quantified statement is true, then you will have to come up with a proof for every single x. So you need to show that px is true for every single value of x. And typically the way proofs for all quantifiers works is you say proof, and we'll come to this later. And the first line you will write is let x be a variable in the domain, a value in the domain. And then the proof will continue from there. So because you want it to be true for every single thing in the domain, you assume that it is an arbitrary thing in the domain. And using this assumption, you try to prove the statement. To show false, on the other hand, for universal quantifiers is really easy. All you have to do is come up with a counterexample. What is a counterexample? Come up with an x, a value in the domain, for which px is false. And as far as logic is concerned, it doesn't care about how you came up with a counterexample. You could have just conjured it out of the blue. As long as px is false, the whole universal quantifier is false. The whole universally quantified predicate statement is false. Ooh, it's not false. So that is your universal quantifier. And then you have the existential quantifier. Here, let me first write an expression. This is written as, remember, a flipped e and then px, and read as there exists an x such that, or there exists an x px. And now here the roles are flipped. So if you wanted to show something is true, then you just need to come with one true value. Here the term that's used is something called witness. So you have to come up with one value which witnesses the fact that px is true. Notice that this is very similar to how we prove falsehood for universal quantifiers, and that's not an accident. We'll come to that in the next video. And if you wanted to show false, now it's tricky. Now you're trying to show that this statement is that there does not exist a single x such that here. So what you actually need to show is that for all x, px is false, right? Because no x works, which means that every single x is the wrong x. And to show this, what you actually need to do is show, or the way the proofs work is here you start let x be a value in domain, and then from here somehow show falsehood of p. So showing false of existential quantifier is similar to showing true for universal quantifier. And again, this is not an accident, they are connected in a very nice way. Okay, so these are universal and existential quantifiers. They are not difficult, but again, I keep saying this, you have to be very precise about their use. As long as you stick to the rules, they're almost trivial. You see a problem and is it true for all x or is it true for some x? That's the only thing, that's the only two ways of differentiating them. If it's true for all x, then you're looking at a universal quantifier. If it's true for some x, then you're looking at an